talking scientific notation. You know that song? Come on. All right. Scientific notation is a way you can represent very large or very small numbers. Okay. So it'll say something like 5 times 10 to the 20th power, or 2.1 times 10 to the negative 30th power. Ooh. So write each expression with a single exponent. These are being multiplied right now. So when you multiply with the same base, you keep the base and you add the exponents. 3 plus 5 is 8. 7 plus 9 is 16. 5 plus negative 3 is 2. Negative 6 plus 3 is negative 3. Now, according to our last thing, that's the question they want answered. They want 10 to the negative third. But just remember, let's refresh from last time. Negative exponents in our final answers typically are a problem. So if we said just simplify this, I would want you to put 1 over 10 to the third or 1 over 1,000. But that's not what they're asking us right now. So don't worry about that. That was just a refresh. So check this out. I know I just said this. Scientific notation, I mean, when we're talking about outer space or the size of atoms or things that are just, they would be enormous numbers if handwritten out completely. So like this number, I don't even know what this number is. Let's see, millions, billions, trillions? 7,500,000,000,000, right? So instead of writing all that, they say 7.5 times 10 to the 12th. So the way you figure out the first number, look, has to be greater than 1, but less than 10. Greater than or equal to 1, but it has to be less than 10. So basically, you're going to have one number in front of the decimal spot. That's all you're allowed with scientific notation. So 7.5 would be if we had the decimal here. So then the exponent on the 10 is how many decimal places do you have to shimmy from where it is to where it would be in scientific notation. So it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it shifted the decimal 12 places. So that's how you get that exponent of 10 to the 12th power. Oh my goodness. Did you know about 4,200,000 people visit the Statue of Liberty every year? Don't even get me started on the number of dogs, birds, and mice. It's wild when you include those. Write this number in scientific notation. So this is essentially a fill-in-the-blank problem. It's always some number times 10 to the some number. So the number in front has to be at least 1, but less than 10. So where could we put the decimal to have just one digit in front of the decimal? And that would be right behind the 4. So it would be 4.2. Now, let's count how many places we have to move it from where it is, because currently 4,200,000, it's 0.00000 forever. So how many places did we move it? 1, 2, 3, 4, 5, 6. So 10 to the 6th. So anytime it is a large number, it's going to have a positive exponent. Anytime it's a tiny decimal, that's going to have a negative exponent. All right, let's try out 3 more. Write these in scientific notation. The decimal would need to be right behind the 5, so 5.45 times 10 to the something power. Let's count how many places from where it is to where it would need to be behind that 5. 1, 2, 3, 4, 5, 6, 7 places times 10 to the 7th. Here, it would have to be behind the 7. 7.23 times 10 to the 1, 2, 3, 4, 5. 10 to the 5th power. And this one would have to be 6.02 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 10 to the 11th. So very large numbers have positive exponents on that 10. Look at this. This is a tiny little decimal, right? 0.00079 in scientific notation. So again, we're filling in 2 blanks. This number has to be at least 1 but less than 10, and then some exponent on that 10. So where could we put the decimal to make this number between 1 and 10? I would have to go here, 7.9. Now this is a tiny number, so we're shimmying the decimal to the right, which means our exponent is going to be negative. So 1, 2, 3, 4, 5 places. We moved it 5 places. That's the formal way to do it. Old hillbilly Mr. Plant's way is count the zeros in front of that 7, including the one that's in front of the decimal. There's 1, 2, 3, 4, 5 zeros in front of it, so that would be your negative exponent, -5. That's the way that's just easier and faster to make. So here, just look at the zeros. 1, 2, 3, there's 4 zeros, so it'll be something times 10 to the -4th. Right? That's pretty easy. So then the number in front would be 2.1. And the formal book way would say you move the decimal 1, 2, 3, 4 places to the right. So it becomes 4 to 10 to the -4. All right. It would have to be 5.0, right? It'd have to be behind the 5. But we could just write 5 times 10 to the negative. Let's count how many zeros. 1, 2, 3, 4, 5, 6, 7, 8 zeros times 10 to the -8. Wow. Decimal would have to go here. 8.03 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11 zeros in front times 10 to the -11. That's not too bad, right? We are going to bring in some properties of exponents, which, thank goodness, we just did that the last couple of class periods. Now we're going to actually stretch out the number and write the gigantic or very small number. So they give it to us in scientific notation, and they want us to go backwards with it. So 10 to the 5th power, we're going to move the decimal to the right now, because this number is going to be getting larger. So if we moved it once, it would become 89. We still have to move it 4 more places, which means there's going to be 4 more zeros behind this. Throw in your commas, 890,000. Now this one has a -6, which means we're going to move it left 6 places. Or just remember Hillbilly Plant's way and say, oh, snap, it's going to have 6 zeros in front of this number. But remember, one of those goes in front of the decimal place. So 0, that's our first 0. 1, 2, 3, 4, 5, 6, and then the 2, 7, 1. You got 3 more here. 3.21 times 10 to the 7th. It's going to be a larger number, so we move it to the right. 1, 2 places. We still need to go 5 more places, so there would be 5 zeros after this. 1, 2, 3, 4, 5. Put in your commas. 32,100,000. This is 10 to the -8th, which means there's going to be 8 zeros in front of it. 1, 2, 3, 4, 5, 6, 7, 8, 5, 9. I've seen this mistake happen in the past, because I always say, like, put in your commas on the big numbers. You don't put commas in decimals. So I'll see kids like start throwing commas every 3 zeros there. That's not proper form. All right, now this one is 10 to the 10th. So we move it 3 times, and it becomes 1,006. That was 3 times, but we need to go 10 places, so there's going to be 7 more zeros. 2, 3, 4, 5, 6, 7. 3, 1, 2, 3, 1, 2, 3. Great. Changing to scientific notation. 0.37 times 10 to the 10th is not in proper scientific notation. Now, if I had a question saying, is it improper? You would say no, because this number has to be between at least 1 but less than 10. So to make that happen, we would have to make it 3.7. Now, the interesting thing about that is The relationship between this and the 10 exponent is if you make one larger, you have to make the other one smaller. So we made 3.37, we made it larger to 3.7. So we have to make the exponent smaller. So it was 10 to the 10th, now it would be 10 to the 9th. That's the easiest way that I can do that problem. Another way is to take what they gave us and write it out in standard form. So this is times 10 to the 10th. So you move it 1, 2, becomes 37. And then we have to do 8 more times. 1, 2, 3, 4, 5, 6, 7, 8. And then after that, convert that number back into proper scientific notation. To me, that's just adding an extra step. If you can just remember, if one gets larger, the other gets smaller. Okay? 453.1. We know that 453.1 should be 4.531. Now we had to make that smaller twice. Because if it was 45, we would only have to make it smaller once. But here it's 453. We had to do it 2 times. So because we made that smaller twice, we have to make the exponent larger twice. So 8 plus 2 would be 10. 16 times 10 to the 5th. We got to make 16 1.6. We made it smaller, so we have to make the exponent larger. 10 to the 6th. We have to make this 0.203 2.03. We had to make that larger, so let's make the exponent smaller. 10 to the 5th. 7,243 should be 7.243. We had to make it smaller 3 times. So we'll make the exponent larger 3 times. 12 plus 3 is 15. Let's add more down here. Order these from least to greatest. Just write them in standard form, get them all into standard form, and then it'll be easier to organize them. So this isn't even in proper scientific notation. So we'd have to move it 8 places to the right. 1, 2, 3 becomes 64. That was 3 times, so we have 5 zeros behind it. 1, 2, 3, 4, 5. So 6,400,000. 312 times 10 to the second. We'd move the decimal 2 places to the right. So 2 more zeros behind, 31,200. And 0.58 times 10 to the 7th. We move it twice, becomes 58. We need 5 more zeros behind it. So least to greatest, the 31,000 is obviously the least. So that would be our smallest. And then we have 5,800,000. This would be our second smallest. And this would be our greatest. Multiply 3 times 10 to the negative 7th and 9 times 10 to the 3rd. Express the result in scientific notation. So a lot of times you'll see it like this. But like we've talked about with the commutative and associative properties, if everything's being multiplied, it doesn't matter the order that you're multiplying it. So let's kind of think of it more like this for now. And let's do what's easiest for us. So scoot down. 3 times 9, easy as pie. 3 times 9 is 27. And then these 10s, they're the same base. So when you multiply with the same base, remember you add the exponents. Negative 7 plus 3 is negative 4. Now is this in proper scientific notation? No. So that 27 is larger than 10. So we're going to make it 2.7. We had to make it smaller. So we need to make the exponent on the 10 larger. Larger than negative 4 would be negative 3. Now you could write the multiplication symbol like the dot like we just did up there. Usually in scientific notation, you're going to see like the multiplication symbol that you used in elementary school and stuff. So it doesn't matter to me which one you write, but that's the way you're typically going to see scientific notation. Now scientific notation is the only place where having a negative exponent is acceptable in your final answer. So you don't need to put 1 over 10 to the 3rd or anything like that, okay? So here we go again. We don't need to stretch this out. You can remember the associative property, which states that you can multiply in any order. So I can do the 4 times 6, 24. And then the tens, 4 plus 6 would be 10. So 24 times 10 to the 10th. We need to make 24 smaller, so make the exponent larger. 7.1 times 8 would be 56.8. We got negative 8 plus 4 is negative 4. That's not the proper scientific notation. It should be 5.68. We had to make that smaller, so make the exponent larger. Larger than negative 4 is negative 3. All right. You guys are always asking me for more word problems about the Great Pyramid of Giza. Well, it's in Egypt, and it contains about 2.3 times 10 to the 6th blocks of stone. On average, each block of stone weighs about 5 times 10 to the 3rd. About how many pounds of stone does the Great Pyramid contain? Now, if I said there were 100 stones, and each one of them weighed 4 pounds, and I said, how much is that altogether? You would do 100 times 4. Each one of them weighs 4 pounds. So we're going to be multiplying this. We're going to be doing 2.3 times 10 to the 6th times 5 times 10 to the 3rd. So if we did 2.3 times 5, let's see, 2 times 5 is 10, 0.3 times 5 is 1.5, so 11.5 times 10 to the 6th times 10 to the 3rd would be 10 to the 9th. That's not proper scientific notation. We need to make that 11 smaller, 1.15. Make the exponent larger, 10 to the 10th. Woo-hoo-hoo! All right. A hydrogen atom has a mass of this. What is the mass of this many hydrogen atoms? Again, we're multiplying them. I don't know what 1.7 times 6 is. 1.73. 1.73. Oh, 1.67. Goodness. 1.67 times 6 is 10.02. And then for our tens, we have 10 to the 3rd and 10 to the negative 27. Negative 27 plus 3 is the negative 24. This is not proper. We need to make this 10 smaller, 1.002. We made that smaller, we make the exponent larger. Negative 23 is larger than negative 24. Those negative ones can get a little trickier when you have to make them larger or smaller. So be careful. We did it.